you and me. Yeah. So, Omid, thank you very much for offering the webinar. Please, you're welcome to share your screen and start. And I apologize that we started a little late, but we had some issues with the internet. Sorry.
Okay. I think you need to. Yeah. Okay, and then. Okay, everything is fine.
Off the microphone as well.
Yes.
Okay, that's fine.
Okay. It's fine. Okay. Thank you so much, Francesco, for the introduction that we didn't record. I see still participants are joining, so but let me share my screen and then you can literally start. Okay, it's my screen. Here. Okay, just let me ask the participant who participated online to confirm that can hear me and see my screen with okay. Yes, okay, I see some good sign. Okay, perfect. Okay, 2025 and the International Year of Quantum Science and Technology, and we are happy that we are also contributing to the with this year and with lots of events that we have. This is, of course, an educational event. It's not a research-based event, but let me first of all show you this previous NITheCS schools on quantum computing that we had in the previous years. We started in 2020 with this quantum computing mini school. It was, I think, the beginning of the COVID. And then we have, this is just a standard quantum computing basics. And then we had also quantum machine learning. It's still in 2020. And then in 2022, we had, again, practical version of that quantum computing with Qiskit. And mine is in PennyLane, so it's a little different. Of course, the basics, the mathematics behind this is the same, but I'm using the different packages. And then last year, we had also two mini schools related to quantum computing. One of them was a little more advanced topic. So if you are interested, after learning the basics from this mini school, you have the material to go for the advanced, to search for the advanced material. One of them was the quantum simulation of closed and open quantum system. And the other one was quantum computing for chemistry, which was from electrons to qubits. That was the fancy name. Probably the first question is, how can you get this Google Colab? Okay, first of all, I use Google Colab because I don't want to spend time to solve your issues with the environment, the ID. Some people use VS Code, some people use Jupyter notebooks, and so I try to just stick to the Google Colab. We don't need to talk about those issues, but you need to have access to this Google Colab. So let me open the chat, and because I sent this Google Colab to my GitHub page, and then let me just quickly open this GitHub page and then share it with you. Okay, this is the GitHub page that you have access to all this material: NITheCS, QSouthAfrica Minischool Introduction to Quantum Computing. Okay, you only see there is just README file and then Jupyter notebook. I'm going to share it in the chat, not with hosts or panelists, with everyone. Okay. Okay, here we go. Now you have access to the material. When I add something or edit something in this Google Colab, there is a very nice feature that you can just go to the file and save a copy in your GitHub. And that's very, very handy and quick way to share what you are coding with your participants. Okay, it's here, and then and there is also a nice feature here. If you click on the notebook, I think there should be yeah, there is an option here, open in Colab. So you can just from the GitHub link that I shared, you can click on the open in Colab, and then you can open it in your Google Colab. Of course, I think you need to have a Gmail or something to use the Google Colab. Okay, this is the basic things that you need to know, and then you can follow with me. Okay, well, when I'm coding, you can follow with me. Okay, that's the previous workshop that we had. You can always check and learn more. We also had in QSouthAfrica and QAfrica, we also had some, you can check these links if you want to connect and follow our events, the future events. We started in 2023, as Francesco mentioned, that we started with this Q bronze material, but we don't have any recording of this session. That's the Q board policy. So we started with Q bronze and Q nickel, and then in 2023, and then that was the second workshop was organized by different countries. And also this one, which was, I think, in 9 countries, non-African countries that you can see here in last year. And these are the links, only just the information, but we don't have any recording session of this. Okay. By the way, and I created a mind map for all the resources and the syllabus that you need for if you are a learner or if you are a teacher, even if you are teaching quantum information, quantum computing, you can use this link to have access to a broad range of materials, which is very useful for you. Okay. When you are working in Google Colab, you don't need to install all the standard packages that we use for the computational or scientific and computational packages like NumPy, SciPy, Matplotlib. You can even, with a very easy like list, you can check what packages has already been installed in your Google Colab. You can see a long list. But of course, PennyLane is not one of them, so you need to install it. Okay, for installing PennyLane is very simple. Just let me just do it because maybe I need to change something during the workshop. So you can just shift enter this or click on this run button to install your PennyLane. I just put this quiet because I don't want a messy message, a lot of messages. Okay, it just usually takes a few seconds. The only things I think you need to install is this one. And then after that, you can basically use your PennyLane in Google Colab. Okay, first things first, let's check the version. I think this is the latest version of the PennyLane that I'm using, is 0.42.2. Then we need to import what we need. Okay, we need the NumPy, the standard numerical packages. Definitely need this. We need Matplotlib. We need for this session, I don't need SciPy, but sometimes you need SciPy. And also I use SymPy for just specifically show you the nice representation of the metrics, but these are not very important. The important thing is the NumPy here. And I also check the version because sometimes there are some conflicts. It's always good to check what version are you using. Anyway, let me just run this. And so basically, if you run those cells, you are sorted with the importing and installation. You shouldn't have any problem as long as you are working in Google Colab, but you are more than welcome to use your IDE, VS Code, Jupyter Notebook, or whatever. Okay, let me close this one. So, and for this mini school, because I want to keep it like an interactive session, I don't have any slides. It's a little different from what I already taught in different events. I don't have any slides or PowerPoint or something. We just want to use directly the PennyLane material that they design, actually. Okay, let me quickly introduce you this nice code book, and actually that can be a good incentive for you to go to the website. Okay, this is the code book that we have. Of course, we cannot finish all of them in just 3 sessions in the mini school, but at least you can learn the roadmap, and then after our mini school, you can start learning. We, for this session and for the next 2 sessions, we are going to touch some part of this code book, but I think it's better to register or sign up in this website. Then you can track your progress when you are reading and coding in this platform. So I highly encourage you to go to the website, and sign up should be a few seconds. Just sign up, and then maybe you can do it after the school, mini school, but you can do it right now. It's very easy. I already signed up, so you can see that should be something, your profile, everything is here. But let's assume that you already signed up to this PennyLane code book map, and then you have, okay, that's the starting point. Okay, there are some modules. You see that this is the first module, Foundation of Quantum Computing. Okay, let's explore together what we have in this Foundation of Quantum Computing. Here we have 3, 4, and 4. It's like around 14 sub-modules. So we are going to start from the very basics. Just assume that you don't have any background in the quantum computing. So let me start from the basics. Okay. You can check what you learn here, and then, but the first step in learning quantum computing is the notion of qubits. Let me little maximize this. Okay, that's better. Okay, in classical computer, we have zeros and ones, and then there are different representation, voltage or transistor that you can use to show zeros and one. But in the quantum computing, we have something which is called qubit or quantum bit, which of course corresponds to the something physical. In this codebook, they didn't mention anything about the physical realization of these qubits, but of course there are some physical systems that can show these qubits, and then you can manipulate. For example, the famous example is the spin of the electron that you can use as a qubit. Any 2-level system that you can create, spin of the photon or the spin of the electron or the polarization of the photon, and then we have some circuit which is called superconducting circuits, and different examples. But my focus is not on the physical realization of those, but just remember, just keep in mind that we have something which is called qubit, any 2-level system. But what is the difference between this qubit and then between this classical computer? The difference is we can have something which is called the superposition of the zeros and one. That's one of the features that the power of quantum computing come from. The other one is entanglement. We will talk about entanglement later. Okay, so that's also a very nice definition, that the quantum computing is the manipulation of qubit to solve problem. It's very simple definition, but I like it. So manipulation, what does it mean, manipulation? You will see in a few minutes that first of all, you need to define your quantum state or qubit, and then you need to manipulate this by applying something which is called unitary gate or unitary matrix. So let's see what is the mathematical representation of the qubit, and then how can we manipulate this? Okay, it's not only text, there are some nice visual representation of the different things that you can see here. Okay. First of all, when you want to start quantum computing, yeah, usually we say you don't need to have a PhD in physics, you don't need to have a PhD in math or this kind of things that usually people start to encourage people to learn, but you need to know a little about linear algebra, okay? And by linear algebra, I mean you need to know how to work with vectors, how to work with matrix, how to multiply matrix vector multiplication. So these are the basic things that you need to know. Just give me a second. Okay. So qubit 0 and qubit 1, as I mentioned, that we can have this as a quantum state and the superposition that I'm going to show you in the next step. So this is something new. If you have a physics background, this is not new for you. But if you don't have physics background, of course, this is something that when, based on my experience, people usually ask, what does it mean, bra, ket, and what is bra, what is ket? But okay, let's keep it simple. Bra is just a column vector, 1, 0, and the ket is only the column vector, 1, 0 or 0, 1, and the bra is just a row vector. And I assume that everyone knows the column and the row vector. And then now we want to play around with these vectors. First operation that you need to know is the inner product of these two vectors. Okay. This is something that people know when they learn basic linear algebra, how to calculate the inner product of a row vector with the column vector. But in physics, we like to write it something like this. Okay. So when you see bra and ket, now you know that this is not something very strange and weird. So this is just a new representation that Dirac used and we physicists also used because it's very practical. So now we know what is bra, what is ket, what is inner product. Another concept is normalization that we need to know because, okay, we define here two quantum states, but you cannot just say, okay, this is my column vector and any column vector is a valid quantum state. No, it's not like this, okay? When you want to have a valid quantum state, it should be normalized. And by normalize means when you calculate the inner product of the vector with itself, with something like this, it should be equal to 1. Okay, you can do it as an exercise or as another example. If instead of 1, 0, you have 1, 1, and if you calculate this, if you calculate this, your answer is not 1, your answer is square root 2. So that 1, 1 is not a valid quantum state, but we can normalize it. Okay, now we know that bracket, and these are the basics. Let me close this one. But the first interesting feature of the quantum state, which we don't have something similar in the classical world, is the notion of superposition. So we already talked about 0 and 1 as a ket and as a column vector, but we can have superposition of these states alpha 0, beta 1. And then you can see that you can also represent it with a column vector. Another new things that, based on my experience when we are teaching to the non-physicists or people who don't have background in physics or math, sometimes this is something new for them, is the complex numbers. I'm not 100% sure, but if you are not familiar with complex numbers, it's just check the basics. We don't need the very advanced complex numbers. You can just check the Wikipedia and then see the basics of complex number. But what we need for this mini school is first of all, we need to know this alpha and beta is complex numbers. And because they are complex, we need to define something which is called complex conjugate. Basically, when you have I, which is an imaginary part of a complex number, it becomes minus I. So, and this alpha beta, we call it amplitude or probability amplitudes. Okay. Let me just go a little, and then, okay, you have access to this. I cannot finish all of them in one session, but you can, you should actually spend time and read this part. And when you have question, maybe you can ask me at the end of this session or the end of next session, but they kind of explain step by step, and they gave you a lot of examples. I don't want to go through all the examples here, but you have some nice examples about, for example, we want to verify that the superposition state is normalized. Okay, as I mentioned here, okay, this is real number, but this is a complex number, and this imaginary part, this is something you need to take into account to calculate this inner product. Okay. Again, this is broad, this is cat, and then you want to calculate the inner product to just show this is normalized. If your answer is 1, then the state is normalized and the quantum state is a valid quantum state. Otherwise, you need to change your quantum state with some coefficient. Okay, that's the concept of superposition. Okay, notion of qubit, how to represent it as a mathematical, how to represent it as a column vector or row vector, it depends on bro or cat, and the superposition. And at the end of the day, you want to, first of all, let's say, creating qubits or creating the states and then putting into superposition. But at the end of the day, you want to measure them. And this is very important. When you measure your quantum state, you only get one single bit of information. So that's why when we want to measure quantum system, quantum circuit, we usually have something which is called the number of shots, which is 1,000, 2,000, 3,000, something like that. Because with one bit of information, you cannot get any important detail of your system. Another things here is you want to calculate the probability. Okay, let's say you have a alpha 0, beta 1, and you want to calculate the probability. We call it measure and observe 0. These are the probability. So alpha modulus square and beta modulus square. This is a little different from the standard absolute magnitude to the power of 2. So this is the alpha square. So you see here is not alpha alpha, is alpha alpha star. Just keep in mind alpha and beta are complex number, and then you need to calculate this to calculate your probability. Okay, and that's a very good example. We will see this in the PennyLane as well, but let's just consider a very simple example. This is a quantum state. First of all, it's normalized, it's okay, it's a valid quantum state. And then we want to calculate the probability of this system to be in 0 or to 1. So this is your alpha, 1/2, and minus square root 3i/2 is your beta. And then by calculating alpha modulus square and beta modulus square, you can calculate the probability of the system being in the 0 or 1. And here you can see this is actually, this is, let me just zoom in. This is your beta and this is your beta star. And then you can see that in a very good example. When you star it, the I becomes minus I. So the minus I becomes I. And then when you multiply this, you get 3/4. And you can do it with the alpha as well. Half multiplied by half, you can 1/4. 3/4 means 45%. And 1/4 means 25%. First of all, if you add the probability of any possible states, it should add up to 1 or 100% if you want to show it in the percent. And you can see here, 3/4 is 45%, 1/4. We didn't calculate here explicitly, but you can, it's very easy. It's alpha star as 25%. So, and keep in mind, this is a very simple example, only 1 qubit. In the real world example, we don't usually use 1 qubit, we usually use multiple qubits. And here, instead of 0 and 1, we will see we have 0, 0, 0, 1, 1, 0, and then we have like bigger states and different probabilities. But the laws, the rules are the same. You want to calculate the probabilities, the rules are the same. Okay, that's the measurement. And I didn't mention about operations, but let's say we created our states, psi. You saw in the previous example, alpha was half, beta was minus square root 3/2i. But now we want to change it. We should do some manipulation to actually calculate something, to solve our problem, and to get from psi to something which is called psi prime, psi 1, psi 2, psi 3. Here, we should use something which is called a unitary matrix, U. And you cannot use any type of matrix in as a quantum gate or as a matrix, as a unitary matrix. We use a specific type of matrix, which is called unitary matrix with this property. U dagger should equal to identity, which is identity matrix. And this indicates the complex conjugate, which I mentioned. I becomes minus I, and then you need to transpose U as well. So U dagger is I, and this is the standard definition. So when you have a unitary matrix, it's a valid quantum gate. Usually when you are working with packages, there are lots of famous, like common built-in gates. Let me just quickly jump to this one. For example, let me just open this. So you don't need to define any U to do your calculation. Yeah, here we have single qubit gates. It's built in PennyLane, but if you are using different packages, usually these are common single qubit gates that you can easily find it in any packages. And you can see the matrix representation here. This is the famous X gate or NOT gate, and this is the famous Hadamard gate. You will see these gates in this mini school a lot. Z, S, T, Y, and these are rotations. But the last three ones are different from the rest because, as you can see here, there are something which is called theta. So there are some parameter here that you need to specify. I don't know, pi/3, pi/4. These are some angles that you need to keep in mind. When you want to define this gates, you need to specify this parameter as well. So this is single qubit gates. You apply these gates on the single qubit. But we have multi-qubit gates as well here in this table. the famous C0 and CZ, you see that these are 2-qubit gates. And when you compare this with the previous one, the single qubit gate is 2x2 2x2 matrix, okay? But here it's 4x4 because we are talking about 2 qubits and control X, control Y, and then, yeah. These are the basic built-in actually single qubit gate and multi-qubit gates in the PennyLane. But the question is, can we define our gate? Yeah, the answer is yes. If it's not one of these, then we can use qubit unitary. I will show you in the Google Colab how to use your specific matrix, which is not part of this table, to define your custom single or 2-qubit gates. Okay, let me back to the unitary gates. Okay, this is your psi, and this is your unitary gates here. Then, okay, it's nice to have the solution here. You want to apply this. Okay, when I said linear algebra, for example, you should know how to multiply a matrix with a vector. This is just a basic linear algebra. So you have a matrix and then you have a vector. You apply this unitary matrix to a valid quantum state to get another quantum state. When you have this, you can write it with the bracket notation as well. And again, if you calculate the probability, 25% you can find the state in one, 75% you can find this state in the state 0. Okay. Let me close this. And then, yeah, okay, let me just summarize with this quantum computing in a nutshell. Yeah, everything is linear algebra. Quantum states are linear combination of zeros and one. Operation performed by matrix. Okay. And then there is something which is likelihood of the qubit being in one of those two states after performing measurement that you will see now in the Google Colab. Okay. This is basically quantum computing in a nutshell. Okay. Good feature about this codebook is, I don't want to solve all of them right now, but you can basically, after learning this material, you can test that you learned this material or not. Okay, there are some something which is called coder size. Probably it's like code plus exercise, and then you can actually try your best to solve this, and then after you submit your solution, you can find there are a solution from the PennyLane as well. Then you can compare that your solution is correct or not. I don't want to solve all of them, but I chose one of them as an example, a simple quantum algorithm, I15. Okay. Okay. Okay, before just jumping, all I'm doing in this mini school is based on simulator. Okay, I don't want to use real quantum computer or providers, but if you are interested, you can click on these links and then see what different real quantum device do we have. For example, you can connect to Amazon bracket to see that we have some companies that are working on different modalities, like this is the ion trap base, this is superconducting base, and this is based on the atom quantum computer, Rydberg atom qubits. Okay, you see, you can have access to different modalities, but it's a little, I think, expensive. So for learning, you don't need to connect to the real quantum devices, but there are some methods that you can connect to these devices. You can check the Microsoft Azure as well. There are some famous companies that provide cloud-based service, like Amazon, like I think this is the Microsoft. Also, you can see IonQ is here, but there are just a bunch of maybe a handful of companies that provide these services. Yeah, of course, we have IBM as well. There are, if you go to the, for example, here, there are some details of the, for example, the number of qubits that you have access, and there are some, if its status is available or not. But for this specific Minischool, I don't touch this part. I just stick to the simulator. Okay, let's just start with this coder size, I15, a simple quantum algorithm. Okay, here is purely Python based, but it's very interesting to see how can we do in the Python and create basically our simulator. But I don't want to use this for the rest of it. This is just one example in one cell. After this example, we will use the standard simulator of PennyLane, but that's also good to know what's going on actually. Okay, what you can see here is a matrix. Actually, it's a Hadamard gate, 1, 1, 1, minus 1, 1, 1, minus 1 divided by square root 2. This is the matrix that we define. And as I mentioned, this is the answer of the coder size. Okay. Then we initialize state, and then our state is, okay, in PennyLane, everything should be a Python function. Just keep in mind, this is something specifically for PennyLane. For other SDK, you don't need to specifically work with this kind of defining function for everything. But for PennyLane, it is. And this is our initial quantum state, which is 1, 0, which is state 0. Okay, as I mentioned, you prepare a qubit in state 0, and this is the state 0. And then we want to apply U. Again, I'm just using purely Python and, of course, NumPy. This is dot product, but you can use dot product, NumPy dot product to multiply a matrix with a vector. So it's like U applying to psi, and then you have apply U. And then you can measure this with a simple trick. I use NumPy absolute magnitude, actually, function, but it works for both real number and complex number. So when you use NumPy, when you use this, you don't need to worry about your state is real or complex. It works for both. And this is exactly what you saw, alpha star or alpha square and beta square. And the outcome measurement is, again, we use something in the NumPy package. This is not the main objective of this Minischool, but I just wanted to show you, first of all, solve one of these coder size, and then show you, if we don't want to use PennyLane, it's also possible to calculate some basic quantum function. And then, okay, this is our, now we have our initial state, which is the ket 0. We can apply U to this state, and then we can measure it. This is when we define here. So we define 3 functions, and now we are using these 3 functions. And we use 100 as like 100 times. As I mentioned, when you measure 1 time, it just gives you 1 bit of information, which is not useful. You need to at least have thousands, but here I used 100. When you actually run this code and then print it, you get a bunch of 10, 10, 10. Okay, that's something in the output you can get from a quantum computer. And then you can put it in a much intuitive way. So I use something, this is a built-in function in Python. Again, I just didn't want to use PennyLane for the first exercise by design. And from this, because we basically, with this U that we define here, we created a uniform superposition of zeros as well. Okay, uniform superposition means when you measure the state of 0 and the measure of the but when you increase this number, so if you measure the zeros, it should be close to 50, and because I chose 100. And when you measure 1, it should be close to 50. So we can do it with some lines of Python codes, and then you can see 52%. Let me just run it. Yeah, it's fine. Okay, you see that when I run it, it changes. Okay, now it's 60. Okay, that's also good things about because I use the RAM. Now you can see that when I run this code, it shows me different results every time, but more or less it should be close to 50%. You can change this, okay? For example, you can use 500, and you see that changes as well. And then because it's 500, I expect to see 241 for one of them, 259 for another one, and then you can basically run this code to get the percent, which is 48, close to 50, and this is 51. And then you can plot the histogram to have some ideas about what's going on exactly. I just did it. Okay. Measurement outcome over 1,000 shots. Okay, I need to change this label over hundreds of 50, 500 shots. But yeah, but it's also fine. You can change this to 1,000. Let me do it now, then I will forget. Okay. Okay. Of course, you can use different unitary metrics to you can play around with this after the session, but you can define your U correspond to not just uniform superposition, non-uniform superposition. 25% state 0, 45, I don't know, 75% state 1. And then you can play around with this to see these results will change. Okay, I think I spoke about this. Single qubit gates, multi-qubit gates, you have this. And okay, this is another, still have time, coder size of I23. Okay, when you finish this, I encourage you to do it before the next session. When you finish this, you can go to the next one. Okay, let me just close this. I think I covered. Okay, you can click on the next and then, okay, so not this one, sorry, this one. Okay, and this is your next step. And then you can check your path here, which is very nice, and where you are and where you are going, all the modules, everything. It's very nice to have to track your progress. And okay. By the way, that was Python based, but we want to use something based on PennyLane. Okay, we want to visualize, we want to use the simulator in the PennyLane, not real quantum hardware, but simulator. Okay. First of all, I haven't shown yet, but when we are talking about quantum computing, we need to show something like quantum circuit. I think I mentioned just a simple Wikipedia page. If you have a little background in logic gates, because this is not something new. We had this in the classical computing, something which is called logic gate or logic circuit, a Boolean function. And then you can see this is very similar to what we have here. So you have input, you have output, you have NOT gate, and, or, and this is a standard course that I think computer scientists usually takes in the undergrad. I don't know, it's optional or mandatory, but this is XOR. Okay, this is not quantum computing. This is classical computing, but you see that we can use the same representation to show our quantum circuit as well. So this is classical. Just let me quickly go to the quantum. Okay, you can see more or less So something similar. You have input for the initial quantum state. You are applying some gate in between, and then you can measure your state at the end. These are single qubit gate H, Rx. You already saw the table for this, the matrix representation of these gates. Okay, now we can just, with one single line of code, you can see your quantum circuit that I will show you in a few minutes. Okay, wire and register. Basically, these are the number of qubit that you have, qubit 0, qubit 1, qubit 2, and usually it's initialized in the state 0, so you don't need to be worried about this. But if you want a specific initial state, you can apply some gates here to get that specific initial state that you are interested in. Of course, we already talked about this, but that's very interesting way to show what does it exactly mean when we say about single qubit gate, this circle, triangle, and these are pentagon is just single qubit gate, and this rectangular shape are 2 qubit gates, 3 qubit. Okay, when the qubits are talking to each other, are connecting, we call it 2 qubit gates. But there is one thing is very important here, in my opinion, is something which is called circuit depth. I don't know if they mentioned here or not. Yeah. So where is that? Okay, basically, when you read a research paper on quantum algorithm, or when they claim that our algorithm is better, or in some metrics, there are different metrics. Okay, if you want to design a new algorithm, number of qubit that you are using is one metric. Okay, you can show, okay, I can do the same computation with less qubit. Okay, that's an advantage for your paper, at least. You can show number of qubits is important, number of single qubit gates is important, number of CNOTs or 2 qubit gates also is important. And another metric is the depth of the circuit. So, for example, here you can see, let me just click on the circuit depth. This is the very basic representation of the depth of the circuit. For example, in this circuit, you can see you have 1, 2, 3, 4, 5, 6, 7, 8 different gates, 2 qubit, 1 qubit, whatever. But the depth of circuit is not 8. The depth of circuit is 1, 2, 3, 4, 5, 6. So basically, the number of parallel operation that you can perform at the same time shows the depth of your circuit, which is one of the important metric that you have for your quantum circuit that you are designing. Okay, let me close this. Circuit depth measurement. Okay, we already spoke about this measurement. I don't see anything new here. And the quantum circuit in PennyLane. So for quantum circuit, first of all, we need to import PennyLane that I did. You just need to do it one time. Everything is Python function. Okay, this is the Python function that you define. If you have some parameters, if you remember, I show you some gates have like angle as a parameter, theta, you need to specify. If you have those, you need to put those parameters here. And you have single qubit operations. For example, you have in the, okay, this is the wire also. Wire here, it means qubits. So wires equals 0 means apply gate number 1 to qubit 0, apply gate number 2 to qubit 1. So wires is exactly qubits. And if your gate is have some parameter, you can use these parameters, specify your parameter and apply it to the gate that you want. And if you are using some 2 qubits gates that I show you in the table, like C0 or whatever you can use. You should specify which exactly. I will show you these examples of 2 qubits or 1 qubit gates in the Google Colab. Okay, and then you can perform measurement. But the last things before quickly running the last example, it's quantum device and QNode. Okay, first of all, this is your quantum simulator in PennyLane. Okay, and for this course, I think we are going to use this default qubit. But if you are doing some advanced quantum calculation, you can use, I think, GPU or different simulator, which is designed for the more advanced calculation. But this default qubit is the basic simulator that we are using for this course. You don't need to change this unless you want to do something more advanced. And this is the number of wires. So this line, we need this to tell our code that this is our simulator. And there are 2 methods. I don't want to explain the first one, but because we usually use the second one, which is decorator, which is called decorator. Okay, let's say we define our simulator, and then we need to use this actually line of code to kind of connect this quantum function that you are writing to the simulator. Okay, so these 2 lines of code we always need. And let's see this in practice, what we learn. I'm just using the exercise number. Okay, I finished this one. This one, okay, I23, which is this one, QNode decorator, okay? And that's the last example of today. Okay, what happened here? I defined the simulator, which is default qubit that I mentioned, and I have 3 wires, which means I have 3 qubits. Okay, I need this line of code to just connect my function to this, my quantum circuit actually to the simulator. Okay, I apply a bunch of gates here. Rx to the qubit 0, Ry to qubit 1, and these theta, phi, and omega is my parameters. I put a barrier here to just separate. There are 2 reasons that we use barrier. One of them is, of course, to have a better, it's like a visual tool to separate part of your circuit. Also, it helps in compilation of your code. I don't want to explain it right now, but just consider as a visual tool right now. And then I apply some C0 gates here. Again, barrier, and then I want to return probability. Okay. Then when you run this code and then print your circuit, this is your probabilities that you have. And because you have, I mentioned here, we have 3 qubits, which means we have 8 possible measurement states, always 2 to the power of number of qubits. 2 to the power of 3 means 8, so we have 8 different probabilities here. And I just wanted to check that if you add them, these are number of numbers for the probability. If you check them, the sum of probabilities is 0.999. I just use the round function to round it up to like a 7 decimal, which is 1. It's always good to check if you are running, you have 3 qubits, 4 qubits, 9 qubits, whatever, check that your probabilities adds up to 1 or not. And the last thing is you want to visualize your circuit. If you use the very basic PennyLane, it's not very nice. It's better to use the little more advanced visualization. And this is your quantum circuit. Let me Okay, now it's better. This is your quantum circuit. You apply your gates and then single qubit gates. I just put the barrier here to make it better visually, and the measurement. And this is also different type of visualization. Yeah, you can specify this parameter here, which I did actually in my code. Okay, let me stop here. Probably there should be some question. I don't want to touch this coder size unitaries in PennyLane, but we have 2 more sessions that we can explain those concepts as well. Okay. Should I check the question that we have?
The questions. You said the second, right? So, Omid, thank you very much. Are the questions for Omid? I see one attendee, Keegan, raised the hand. Keegan, you can unmute and ask your question if you want.
It's been resolved.
I don't know. Okay, let me read the question in the chat. First question is, can we run PennyLane code on IBM Quantum, or this later only supports Qiskit? Oh, there are some plugins. I will show you next session that you can connect PennyLane with different platforms. I think, yeah, it's possible. May you please read an equation which begins with 0 so that I may understand the notation better, and may you please re-explain the matrix representation of Dirac form 0. Or may you please interpret the final picture circuit. Okay, first of all, let me answer your second question. Final picture, I assume that you mean this picture, right? Okay, let me explain this one. So, as I mentioned, you have some qubits that start from 0, because Python starts from 0. Okay. Qubit 0, qubit 1, qubit 2, and then we apply some gates, single qubit gates that only apply to just 1 qubit, Rx, Ry, Rz, and we specify some parameters because these are rotation that needs parameters. And then we show with this. Oh, it's good that I just want to check that you see my mouse or not. And then I just put barrier, it's not important. And these are 2 qubit gates, which is C0, C0, and the C0. I didn't explain a lot about this, but you just consider qubit can interact. Okay, we will talk about C0 later, next session. And then we measure it. When you measure it, then you have some probability that I explained in the first example without using PennyLane. And I didn't get the first question. Equation begin with which equation? May I understand the notation better? May you please re-explain the matrix representation of Dirac form? Matrix representation of Dirac form. Which part? Yes. Because in Dirac form, I mentioned that for the qubit, you have like 0 and 1, and then you can define your 0 and 1 as a column vector. Your matrix that you mentioned is like a 2x2 matrix for one single qubit. Okay, then you want to multiply them to get a new state. But maybe you can a little elaborate your question, that when I finish the rest of the question, I will back to your question again. Okay. And Mangaliso Lamini, please repeat on the wires as states wire 2 becomes 0.0001 to the power of t. Sorry, I didn't get that question as well. If somebody can help me with the second question. I'm not sure what do you mean by 0.0001 to the power of t, but you have the code and you are more than welcome to play around with this code, okay? Let me just explain the last question. My question is, what are the most advanced application of quantum computing nowadays, and what opportunity for non-physics to learn it? I'm a climate data engineer making a PhD on machine learning and climate. Okay, quantum computing actually has a lot of different applications in different sectors. Actually, one of them is climate change. In healthcare system, in pharma industry, chemistry, drug discovery, finance, a lot of hope in optimization when it comes to logistics. Yeah, we have a lot of sectors that are interested to invest in quantum computing to solve this problem. But at the moment, we don't have practical quantum advantage. So if you have a problem, you can solve it with the classical system as well. But in the maybe not very far future, we will have some algorithm that can solve a problem that probably a classical computer cannot solve it. So if you are a PhD on machine learning and climate, maybe you can do a postdoc on application of quantum computing in climate change. Okay. Please, I cannot reach this page of the coding through the link that you share on the chat. Can you put the link that send us this coding page? Okay. So it should work. It worked. Okay. I'm just putting it again. Okay. Maybe you missed the first part, but even you just need to click on here. I'm just explaining again. You just need to click here, and then when you open this notebook in the GitHub, of course, in GitHub you cannot run your code. You need to open it in Colab. Just click. It shouldn't be a big problem, and then you can open it. I just made it as easy as possible. I'm just putting it again. Okay. I am think you are explaining circuit. Okay, I mean to ask, what type of vector does 0 represent? Okay, the 0 is just 1 0. Okay, you have a column vector 1, first entry, 0, second entry. You may read any equation that begins with 0 that you read in the first part of the class. Okay, let me just quickly open this that you mentioned. I don't know what part. Okay. Can I stop and okay, you made me host. Perfect. Thank you so much. Okay. Okay, I'm host now, and then I can end the session. Okay. Thank you. And by the way, let me just quickly go here. Okay, I explain here the mathematical representation of the qubits, right? Okay, you have this qubit state 0, state 1, and then you can manipulate these qubits with, maybe you can read this part of the codebook, and if you still don't get what's going on in the linear algebra part, maybe you can just ask me next session. Because we are a little above. Okay, Benjamin, how do we get access to the learning material? I think, put it into the chat. Benjamin, just check the chat and then open it. Please, I cannot reach this page. Okay, I just already answered. Thank you so much. I think, yeah, if there are no more questions, then we can end the meeting here and see you next week. Stop sharing. Okay, thank you so much. Thank you.